Okay, since we've been using computers, we've had this issue where all the traffic has to go through the operating system. It's kind of been a fact of life. And that was great when you couldn't necessarily trust the users, you couldn't trust the software, you didn't know where stuff was coming from. And in an uncontrolled environment, the kernel and the operating system was kind of the trust factor in the middle, and it managed and controlled all of this stuff. That was great until we started really worrying about performance I/O, right? And moving vast volumes of data through the system incredibly fast. So the HPC guys kind of cracked the code on this back in the mid-90s as Linux clusters were starting to evolve, 96, 97 timeframe. And what they came up with was the concept of kernel bypass. They basically said, hey, we have a network adapter, and what we're going to do is we're going to short circuit the path from the network adapter into user space and hand the data directly to the application without having to go through kind of the kernel and all of that nonsense, because we trust this particular data coming from this particular port, right? And that was fine when it was a finite problem on a kind of funky network, InfiniBand or, MirrorNet or Quadrix or, C-stars or any of those other things. But as you get into the real world, around 2009, we said, hey, wouldn't it be kind of cool if we could take those HPC concepts and move them to traditional business applications, right? And electronic trading was the one that really kind of where the money was. And we looked at accelerating that. And so we were accelerating both UDP and TCP traffic directly through the network adapter and straight into memory. And the benefit of doing this back in the 2009 or 10 timeframe, on a 10 gig adapter, you were looking at a 15 to 17 microsecond half round trip, right, for typical UDP, TCP traffic. When we went and began doing this at Miracom at that time, we were getting it down to around 4-ish microseconds. So that was a huge gain, right? It's since been squished down through Solarflare down to sub 1 microsecond in the 870, 900 nanosecond range, right? So this stuff is incredibly fast. A normal 10 gig adapter today is probably in the range of about 5 microseconds, right, for a half round trip, which is a receive and a send, right? So kernel bypass is kind of the key to that space. The problem is when you do kernel bypass, you lose all that security that you get from the kernel. So we'll get to how to fix that. This is one example of the half a dozen or more apps that are kind of Web 2.0 apps that we demonstrated accelerated performance on. We've done it for Nginx and Redis and HA Proxy and so forth. This is the performance difference for NettyIO. Netty is a Java app server interface. We saw about a 70% increase in performance when we went from regular kernel I/O to kernel bypass. We have some applications like Nginx in reverse proxy mode where we can see up to 400% application boost, right? So we're talking significant gains in performance. So we've proven this, in FinTech with databases, software load balancers, reverse proxies and all those other things. But again, we lose security for performance. So we're going to get to how to do the security thing in a second. Let's go take a look at storage next and how we accelerate storage. So we've all lived through this part of it. Spinning disks were great when they were around for 40 years. And then we moved to SSDs. SSDs obviously introduced several orders of magnitude improvement in performance. They introduced a whole nother set of things with parallel queues and much deeper queues for commands. And then we have storage class memory. And all this stuff has dramatically improved performance. The problem is when you start running this stuff over a network, right, you want to also have a high performance network to do that, right? And so NVMe OF came about. We've been working on this for the last 3 or 4 years. NVMe OF is obviously available in a variety of different flavors. We come at it from kind of the NVMe over TCP approach. We were the first ones to do that. Some big social network asked us if we could. We did. We then took that code and donated it or contributed it to the NVMe consortium. And we've since helped iterate that a few times. And then we also have a kernel bypass version of this as well, right? You can run it on both the target or the initiator. And this gives you kernel bypass performance for NVMe traffic. So doing some testing on this using high performance networks, we essentially saw basically 99 microseconds, random 4K read. We have some instances where we've gotten significantly below that on a Samsung drive. This data is about a year old. I haven't been able to get new data yet. But the point is, here we've gone and used kernel bypass to accelerate storage, but again, we lose kind of the security methodology, that is wrapped around all the access for this stuff. If you actually line it up to NVMe, against TCP and RDMA, it basically all kind of stacks up from the same performance point of view. So now let's go into hardware-based acceleration, right? So as I mentioned before, I'm with an FPGA company. There are three ways that you get your data processed. You got basically three: CPU, GPU, FPGA, right? McDonald's, Taco Bell, Chick-fil-A, right? Depends upon how you look at the world, I guess. You could say AMD is over there. They're like Burger King, right? Number two, right? Things have changed a lot in the last few years. FPGAs have gotten bigger, they've gotten faster. We've got system on a chip stuff that they've rebranded with some other name. But these things are getting to be at the high end of the acceleration curve. And we're starting to see applications where I'm working on one now, video streaming, right? We've got 7 FPGA accelerators in the box and, one Opteron or, AMD processor just for the I/O, for managing the PCI Express channels. And we're accelerating, live streaming, right? Twitch and things like that, where, the data is coming in and it needs to be decoded and then transcoded, and you had to run through an A/B ladder and deliver it in a bunch of different formats. The point is, the world of acceleration is going to fall to those basic three areas, right? And FPGAs are going to take over a lot more of it than they have in the past. We've accelerated a number of applications with FPGAs directly. Problem is the same as kernel bypass, though, right? The moment you start accelerating these apps, where you're routing the traffic directly from the network through the FPGA, accelerating it, shooting it back out, you lose the security aspect of all of this stuff, right? Some performance gains, just to kind of give you a taste of all of it. 2 to 30 times acceleration, depending on the app, right? Average is typically around 4 to 5 times performance benefit. Okay, here's what you're all here for, and I'm going to keep it short and sweet so we can all be out of here soon. Keys to hardware-based security. Now, at this point in the presentation 3 months ago, when I submitted the title and the abstract, I had a product that I wasn't going to pitch the product, but I was going to go over high-level concepts and kind of walk you through it and tell you how all the things I just mentioned could be solved in hardware at the NIC, right? But instead, since I don't have a product anymore, yeah, someone took the rug totally out from under my feet. I'm going to talk about the aspects that would make for a really good way to do this, if you were to do this, right? And give you a vision of what you're going to see a year from now in something else, probably. Okay, so keys to hardware-based security on the system. It starts with, and how many of you were here for the previous talk? A couple of you. Okay, good, because I'm the key on a couple of those things. First one is Tamper Resistant NIC platform. Okay, and I'm going to go into that in a second. That's vital to the whole thing. If you don't have a Tamper Resistant NIC, then all of this stuff is a bunch of baloney, right? You need enforcement to be done in the NIC. It cannot be done in an app running on the x86 anywhere in order for it to be effective. The telemetry is also included in that bucket, right? You need a way to take that data and the control and get it to the NIC from a central location in a secure manner, and then you need a central location, obviously, to direct and manage all this stuff. Okay, tamper-resistant NIC firmware. The previous speaker talked about this. He touched on it and then kind of like took off, right? What you need to do is you need to have the firmware in the network adapter be digitally signed. Typical standard these days is a 384-bit elliptic curve cryptography signature, which basically says they take the firmware, They sign it in a way that there's a 384-bit signature. And any way, if you change the firmware in any way, right, the signature will no longer match when the firmware is actually loaded. What happens is, before the NIC begins loading the firmware, it has in hardware some stuff that says, hey, let me compare the signature I have for that firmware against the firmware, and if it aligns, then I'll load it. If it doesn't align, I brick the NIC, game over, the adapter is offline. Now, you ask yourself, have we actually tested this, right? I had a security advisory board, and one of my security advisory board members actually had some of our NICs, because I gave them all NICs. And he went home and he took the NIC out, put a clamp on the chips, took the firmware off the NIC, twiddled a few bits, put it back on the NIC, brought the NIC up. It was bricked, like it's supposed to be. Took it back out, put the good firmware back on, put it back in the server, and it worked. Not good. You'd say that's good, right? Because, okay, the firmware is now legit. All right, the signature matches the firmware and everything's happy and hunky-dory. The reality is, if we were truly secure, we would have stored the fact that we had an invalid boot attempt, right, with bad firmware. And then on the boot with the good firmware, we would have said, okay, we're gonna let you come up this time, right? But we had this bad occurrence, and you gotta take care of that because maybe the next time we're not gonna let you boot it until you fix it, right? So you need tamper-resistant firmware that's signed and checked. You need to log these attempts. The NIC also has to be able to agentlessly establish a secure connection to some sort of central command and control server, right? What I mean by that is it has to be able to set up an SSL TLS connection to a central server and be able to use that secure channel to share data back and forth between them. The reason why you want to do it all in the NIC, right, and this is kind of critical to the whole thing, is as a hacker, I didn't mention this. I'm a CISSP. Does anybody know what that is? Okay, a couple of you do. A Certified Information Systems Security Professional, which means I took a really hard test to prove that I kind of know what I'm talking about. So as a hacker, right, the first thing I do when I get onto a box is I escalate my privileges to root, right, if I can pull that off. And then the next thing I do is I turn off all the logging, right, do what I need to do, look to see if there's anything else I might have missed logging-wise and clean it up, and then turn logging back on and then get the hell out of Dodge, right? And in the middle of all of that, obviously, I'm going to turn off any firewalls on the server, right, because I don't want to be blocked or tracked in any way, right? Once someone gets root on a server, all bets are off if your security is in software, because they'll find the software, they'll do a PS minus AE, right, and they'll watch what goes by, or they'll grep it for the key things that they normally look for, and they're going to turn the stuff off, and then logging is going to be off, and it's not a security solution on an endpoint if it's done in software, because it can be beat, right? If you're doing it in the NIC, and what we were doing at the time was, as soon as the NIC was bound, right, there was a simple process we ran once. It binds the NIC to a central control server. We would tear down the local control plane for the security functions in the NIC, so that no matter what authority you had on that server the NIC was in, and even if you were a Solarflare developer who knew the exact MCDI commands that they could use, right, to manipulate the NIC, they couldn't go in and make any changes because those command paths were torn down, right? So it really was kind of a zero attackable surface area on the NIC itself. And that is kind of one of the keys to this whole thing is reducing the surface area of an attack, right? And getting it down to almost zero is about as good as it's going to get. And then a binding process is the last thing I mentioned, which is once you establish that secure control plane back and forth between the NIC and the central control point, you need to lock that process down and make it permanent. Okay. Agentless enforcement telemetry. Okay, so not only do you need the control, a lot of the stuff to happen in the NIC, but you actually need the enforcement to happen within the NIC itself. And what we were doing at the time was the NIC actually maintained a table of up to 5,000 entries. It was a hash table, and we could hash on the 5-tuple, right? The 5-tuple is source and destination, address, port, and protocol, right? So we could hash on that, see if it hit the hash table. If it did, then we can look for the action that was associated with that hash entry, whether it was accept it or drop it. And then you could also log it. And what that allowed us to do is to hardware filter all the traffic that was entering the box and leaving the box, without missing a beat on any of it, right? And so there were several cool aspects to that, right? It was wicked fast, right? How many people here have used a Fortinet, right? It's one of the fastest firewalls out there, right? 2.5, 3.5 microseconds for packet to traverse through the firewall because it's got a lot of stuff it's got to go through. We were doing this, the hashing aspect of it in about 250 nanoseconds, right? So we're, an order of magnitude faster from more or less than the Fortinets, and this was actually in the NIC itself. Filtering, also we were able to do alerting. How we do that, obviously, is we would, be able to send a message back to the central controller and say, hey, I let this packet go by, but you said you wanted to be alerted on it, so here it is, this is a flow that showed up that you were, wanted to be aware of. You have to support millions of rules. We were only able to do about 5,000 in the NIC, and that was kind of the Achilles heel of the problem, right? If you can only do 5,000, you're a good internal solution within the data center for traffic within the data center. The moment you want to be an edge solution for web and things like that, you need to support millions because honestly there are millions of bad actors out there and the tables are constantly getting updated. Let's see. You also have to be able to report flows to the central controller, right? And that means not only new flows, but you also have to report byte counts, packet counts, flow rates. How often am I getting the packets? Because you want to look for attacks on all of these vectors, right? So it's really important that all this stuff gets done in the NIC because A, you don't want the host to have to be bothered with it. B, you don't want anybody to be able to see it on the host and know that it's even happening, right? Because if it happens in the NIC, if I'm a hacker and I'm on the server, right, and I somehow made it on the server, right, or I'm a malicious insider, right? I walked up I have access to the data center. I walked up to the server. I have user IDs and passwords, and I decide I want to exfiltrate some data, so I SCP my file from. I try to SCP my file from here to my desktop and then realize I can't make a connection because the packets are getting thrown away and it's destination unknown type of thing. So you want to be able to track all this stuff and you want it done in the NIC. Secure control plane obviously has to exist so that the NIC can exchange data directly with the central controller. And it's where the central controller is where you're defining your roles and your policies, you're defining your hosts and host groups. And you're basically attaching all of those things together to give you one unified policy that you can then centrally manage. And as I mentioned, the central orchestration has to be in the form of an SDN neutron-like controller, right? Something that's got RESTful API interface so that you can tie other systems into it. You can get value out of it beyond just the management aspect of it. So for example, one of the things we were doing was we were exporting all the flow data to Splunk, right? So just in case we missed something, that we had enterprise tools that could then scrub through all the Splunk data and look for patterns that we weren't able to carry or detect. You want this centralized orchestration facility to have an object repository where it's clustered such that if any element goes down, obviously you have the fault tolerance of having other elements up and running. So typically databases like CouchDB are good for this. You can cluster up to 4 nodes. You also want to play some tricks with logging, right? You want to write your logs to the standard places so that your standard tools can get to it, but you also want to write them someplace else that you don't tell anybody about. Because God forbid somebody gets on your central control server and decides, okay, I've got authority to run this orchestration system and I'm going to turn off this aspect and I'm going to do this and then I'm going to turn it back on and that way nobody will know I did it, right? Well, the moment somebody says, hey, wait, we found out something got stolen, we go back into the system, there's no record of it, they call us up and say, hey, yo, there's no record of this, how did this happen? We'd say, oh, hold on, and we'd go to the other set of books, right, and look and say, well, someone turned off logging at this point in time, and it was this guy, right, and then he did this stuff, and then he turned logging back on, right? And so your central tools and central logging mechanisms are great because they can get fed into all of your log management systems. But having another copy of what's going on is kind of critical to this whole approach to things. Okay, so this is pretty much the meat of the whole thing, right? Why hardware enforcement, right? You know, we've talked about this already. Software enforcement is fairly easy these days to defeat. You have to kind of do it in hardware. If you do it in hardware, it's transparent to the root user, right? So the root user comes on and all he sees is symptoms of why he can't get his stuff off if he got on and was able to escalate his privileges. That's even assuming he was able to get on, right? Another critical thing is, you know, it adds a whole layer of, you know, enforcement in hardware to that security onion, right? We've all seen the security onion. We all know there's all these layers of gobbledygook out there, right? And so this kind of helps add another layer to all of that. You know, what typically would happen is, you know, you get a phishing email, you know, somebody gets compromised. Once they get compromised, the rootkit ends up on that particular poor person's laptop or desktop, right? The rootkit then allows the attacker to easily zip right past all the firewalls, get in, do what they need to do. And once they're on that poor person's machine that's been compromised, right, they're going to say, hey, what servers does this person have access to? Oh, they have access to those. Okay, I'll use their credentials to go out to those servers, see what I can see, and see what access those servers have to other servers, and I'll build a tree and figure out how I'm going to attack things. This allows you to kind of cut a lot of that off at the head. Because again, you don't have any attackable surface area. In doing this approach, if you do enforcement in the NIC and you kind of clamp down on the enforcement, you can actually, you know, to steal a metaphor from Star Trek or from Harry Potter, you can cloak the servers in such a way that you can only see them if you know the exact service ports that those servers are using, right? So if anybody's using a port scanner or any sort of tool to enumerate the network, right, what ends up happening is they'll hit a server that this stuff is running on, and the traffic will come in, and the traffic will get dropped. Unlike IP tables or NF tables or, you know, any of those other ones, they usually send back a packet that basically says, oh, you're not allowed to do that. Well, now you know something's there because you got a packet back, right? With something like this, we drop the packet, and it looks like network dark space. You can't attack something if you can't see it. Now, you know, if you end up hitting the production port, then you'll be like, wait a second, hold on. I found that port 80 was open, but I swept past all these other ports and I got nothing back. Something's a little weird, right? If you're savvy, you'll say something's weird. If you're not that savvy, you'll be like, whatever, right? And then the final issue is if you do it in hardware, you've got extremely high performance typically. This stuff is done in ASICs. It's done incredibly fast. It will soon be done in FPGAs. And that's the last and final slide, right, is the rise of the smart NICs. They were talked about once or twice earlier today. I've been involved in smart NICs for the last 4 or 5 years. You know, doing them in ASICs, doing them in smarter silicon that has either processors or FPGAs is the way to go. You're going to see a lot of these popping up in the next couple of years. There have been some in the recent past. Bluefield, people know about Bluefield. Bluefield 2, Bluefield 2 got better. Okay, if you're familiar with Bluefield, you probably aren't familiar with where it came from, right? It was originally Tylera, and actually it was even an MIT project before it was Tylera, right? These things are hard to do, but you know, once you get them right and you do them in the hardware of the smart NIC, you know, you get the blazing fast performance, you get the server cloaking, you know, and you get the additional layer of security in hardware. So that's kind of it. If you guys have questions, I can go as deep as you want to go on some of this stuff. I can't tell you the product, although if you go backwards in some of my blog entries, you'll probably find the name of it. Or I can, you know, explain to you, you know, if you want to know more about where it's going to go, I can probably enlighten you where it might go.
A statement on this, where might be heading?
Sure. Okay, so IP tables is kind of the de facto way everybody does it in software. The problem is it's not very fast, right? And they've tried to do things to make it faster. XDP and other things have definitely sped it up. What you're going to see is IP tables is going to reappear inside the NIC, right? And you'll be able to load eBPF or other things. into the NIC in such a way that you'd be able to take what you already have and move it down into the NIC and have it managed centrally from that point of view, right? You'll see things like Calico or Tigera, if you're familiar with those network overlay systems. Calico provides a network overlay for Docker and Kubernetes, actually Kubernetes really. And you'll see the security model for that move into the NICs themselves, right, and be managed through etcd directly down through the central controller and out to the NICs probably. So you'll see, IP tables in the NIC. You'll probably see a few other interesting things show up. Personally, I would like to see something called moving target IPv6 defense. Anybody know what that is? No, this is freaking cool. And it can only be done with a smart NIC, right? And it hasn't appeared anywhere yet. There was a paper written back in 2011 on the concept. You'll have keys for your car where you can unlock the door remotely for the car. That uses a rolling code algorithm, right? There are ways to hack the rolling code algorithm, but they're really just replay attacks, and it's nothing that elegant, right? Imagine if, from your application on your server's perspective, everything's the same, right? Nothing changes. But your NIC, under the covers every 10 milliseconds or so, changes its IP address, and it changes the port for that application. And everything else on the network, the other NICs on the network, know the algorithm that all this stuff is going through. And it's using IPv6, so it's using these big addresses, right, which aren't really humanly manageable or readable for the most part. And it's constantly rolling through addresses and rolling through ports, right? Any attacker that clamps onto the network and is using Wireshark or any Wireshark-like knockoff to look at the packets is not going to be able to make heads or tails of what the heck is going on, because every 10 milliseconds stuff is switching, and he'll think, oh, I got port 80. No, wait, that wasn't port 80 traffic. It's on port 4786. Oh, wait, no, it's over here now. It's over there now, right? And there's no way that they can track what the heck is actually going on. But you can only do that if you have a really smart NIC, because it has to do it at a kind of an overlay level, right, where it's basically encapsulating the packet, maybe even use an overlay network, but encapsulating the packet, and it's dynamically handling all of that addressing changing, right? So you'll probably see that in a couple of years from somewhere, somebody, can't tell you who. But, so it's moving target IPv6. You can look it up on the internet. It's a really cool paper. Other things, questions? Yeah.
Any statement of what may happen with prior product ideas? New ownership? Repeat your question.
Yeah, so there was originally a product that was underneath some of this discussion that's no longer part of that, right? Xilinx chose not to move that product forward at this time, but that doesn't mean it's dead. It just means it's on the shelf, right? So at some point in the future, when the smart NICs rise up enough where you've got a lot of things to manage, right, that may actually rear its head again and come back and just have to get dusted off and cleaned up a little bit. That's probably what's going to happen in a year or two, I would say. I don't know for sure, right? But I'm surprised we haven't seen this come from anybody else yet. I mean, who else is doing, hardware security in a NIC, right? I mean, you theoretically can do it with most of today's NICs, but it's hard to do centrally, right? That's really the kind of the key to the whole thing is, doing it centrally. Because doing it locally, it's not a security solution. We actually had a local version of this, and I would not allow them to go beyond calling it a filtering solution, right? Oh yeah, you can filter packets, but anybody knows what's going on, they can get root access to the box, and they can see what the heck you're actually doing, because it was local and it was only filtering, right? So you have to do it centrally and lock it. Yes?
What do you see in the way of IPsec and DNSSec?
What do I see in the way of IPsec?
The question is, how much penetration is there and how useful is it? Those two questions.
Yeah, that's a good question. I'd say it's going to come inside the enterprise, the bigger enterprises first, obviously. It is needed, right? Because it is so easy from an attacker's point of view once you have a toehold, to see what the hell's going on. You fire Wireshark up, log the things that look interesting, and then just cut it up and decide what to do. And with IPsec and DNS, you can get rid of some of that. Yes.
Actually starts with MACsec, Mac layer security.
MACsec, yeah.
Some of the hyperscalers who have government contracts, so you can't touch it at all.
So you don't get on the network unless your Mac is registered.
Yeah.
Mac address is registered.
Even if you're registered, you can't see the other guy's packets. And European universities are doing exactly the same thing for liability. So Mac layer encryption.
All right. There you go. Any other questions? I'm here for you guys. Okay. That's it, really, for me. Thanks again. I hope you had a great day. And see you next year.